You didn't choose to be born. You didn't choose this planet, its atmosphere, or its place in the solar system. You didn't design the water in your cells or the gravity that holds you here. Yet everything around you works with a precision that's hard to believe. The air you breathe is mostly nitrogen, with enough oxygen to keep you alive and a trace of carbon dioxide to feed the plants. Shift that balance slightly and life disappears. Water behaves oddly when it freezes. It floats, a quirk that keeps lakes alive through winter. And Earth's distance from the sun lies in the narrow band where liquid water can exist. A little closer and the oceans boil. A little farther and the world freezes. So settle in and let your mind drift between what you assume and what might be true. Tonight we explore a question that changes everything. What if none of this is an accident? What if Earth wasn't just lucky, but built? Let's start with something simple. Your body. Right now, as you're sitting here, your cells are pulling oxygen from the air around you, moving it through your bloodstream, feeding your brain, keeping your thoughts alive. You didn't design that system and you don't control it, but it happens every moment without you thinking about it. And it only happens because the air contains exactly the right amount of oxygen, about 21% of the atmosphere. If the oxygen level were 25% instead, a single spark would turn forest into fireballs, and lightning strikes would ignite the atmosphere itself. The world would burn faster than anything could evolve to survive it. If it were 15%, you'd suffocate slowly as your brain dimmed and your muscles weakened, making complex life as you know it impossible. But it's not too high, and it's not too low. It's 21%, and it's been stable for millions of years. The rest of the air is mostly nitrogen, about 78% of what you breathe. Nitrogen doesn't do anything for you directly, because your body can't use it, but it dilutes the oxygen just enough to keep everything from catching fire. It's a buffer, a stabilizer, and without it, the air you breathe would kill you. Then there's carbon dioxide, less than 1% of the atmosphere. Any more, and the planet overheats. Any less, and plants stop growing, and those plants produce the oxygen you need while anchoring the entire food chain you depend on. It's a three-part mixture that has to stay in balance, and somehow it does. You've been breathing this air your entire life without thinking about it, but pause for a moment and notice that the thing keeping you alive right now is a chemical cocktail mixed to a tolerance most laboratories couldn't match. Now let's talk about water. About 60% of your body is water, flowing through your blood, filling your cells, surrounding your brain. You are, in a very real sense, a bag of water that learned to think. And water behaves in ways that make it far more than just a simple chemical compound. Most liquids get denser as they cool, contracting and sinking as the temperature drops. Water does too, but only until it hits 4 degrees Celsius. Then something strange happens. It reverses course and begins to expand as it freezes. That's why ice floats, something you've seen 1,000 times in glasses and frozen lakes, and it seems normal because it's familiar. But it's not normal at all. It's rare, and if water didn't do this, you wouldn't be here. Here's why that matters. When lakes freeze in winter, they freeze from the top down, because the ice forms a layer on the surface, while the water beneath stays liquid. Fish survive, ecosystems persist, and life continues through the cold months. If ice sank the way most frozen substances do, lakes would freeze from the bottom up with ice piling on the lakebed, until eventually the entire body of water turned solid. Everything in it would die, and every winter would become an extinction event. But ice floats, and so life survives. That's not the only unusual thing water does. Water has what's called a high specific heat, which means it takes a lot of energy to change its temperature. This property turns oceans and lakes into thermal buffers that absorb heat in summer and release it in winter, smoothing out the temperature swings that would otherwise make most of the planet unlivable. Without that buffering effect, the difference between day and night, or summer and winter, would be far more severe than what we experience. Water is also one of the best solvents in the universe, capable of dissolving more substances than almost any other liquid. This allows it to carry minerals, nutrients, and gases through soil, through rivers, and through your bloodstream, enabling every chemical reaction your body depends on. Inside your cells, water moves substances in and out, transports hormones, regulates temperature, and helps maintain structure. Your cells simply wouldn't function without it. All of this, the floating ice, the heat regulation, the dissolving of nutrients, comes from one thing: the angle between two hydrogen atoms and one oxygen atom in a water molecule. If that angle were slightly different, water would behave like any other liquid, freezing solid in winter, failing to stabilize temperature, and unable to carry the chemistry that life depends on. But the angle is what it is, and because of that, you're here. Now zoom out from your body, away from the air and water you depend on, out to where Earth sits in the vastness of space. You're on a planet orbiting a star, and that star, our Sun, is stable, medium-sized, and burns steadily for billions of years. Not all stars behave this way. Some flare unpredictably, blasting their planets with radiation that strips away atmospheres and makes life impossible. Some burn through their fuel too quickly, dying before complex life has time to evolve on any worlds that might orbit them. But this star is different. It's steady, reliable, and predictable, providing a constant source of energy for billions of years. Earth orbits this star at a distance of 93 million miles, and that number is far from arbitrary. Scientists call the region around a star where liquid water can exist the habitable zone, and it's a surprisingly narrow band. Too close to the star and water boils away into steam. Too far and it freezes into solid ice. Earth sits right in the middle of this zone, in what's often called the Goldilocks position, not too hot and not too cold. If Earth were just 5% closer to the Sun, the oceans would begin to evaporate and the atmosphere would thicken with steam, triggering a runaway greenhouse effect that would turn the planet into something like Venus. On Venus, surface temperatures are hot enough to melt lead, and the sky rains sulfuric acid, making it one of the most hostile environments in the solar system. If Earth were 5% farther from the Sun, the oceans would freeze over and the planet would lock into a permanent ice age. Glaciers would cover the continents, and life, if it existed at all, would be limited to simple microbial forms with no chance of developing complexity. But Earth isn't 5% closer or farther. It's right here, in the zone where water stays liquid, where temperatures allow for seasons without catastrophic extremes, and where life can take root, grow, diversify, and eventually produce something capable of asking why any of this exists in the first place. And it's not just about the distance from the Sun. Earth's orbit around the Sun is nearly circular, which means the amount of sunlight the planet receives stays relatively constant throughout the year. Some planets have highly elliptical orbits that bring them very close to their star during one part of the year and fling them far away during another, causing extreme temperature swings that make stable climates impossible. Earth's nearly circular orbit provides the kind of consistency that allows climates to stay within a range that life can adapt to over millions of years. Once again, it didn't have to be this way, but it is. Now let's go deeper, beneath the surface, into the structure of the planet itself. At the centre of Earth is a core made mostly of iron and nickel, divided into two parts, a solid inner core and a liquid outer core. The outer core is in constant motion, swirling like a massive ocean of molten metal, and that motion generates something you can't see or feel but absolutely depend on: Earth's magnetic field. This invisible shield wraps around the entire planet, and it's the only reason you can walk outside without being killed by radiation. Space is not empty. It's filled with high-energy particles streaming out from the Sun and from distant cosmic events, and these particles are small, fast, and destructive. When they hit living cells, they damage DNA, and enough exposure makes life impossible. Earth's magnetic field deflects most of this radiation, bending the particles away and sending them harmlessly into space, and it's been doing this job for billions of years without pause. Mars offers a stark lesson in what happens when a planet loses this protection. Mars is smaller than Earth, and because it's smaller, it cooled faster. Its core stopped churning, the magnetic field collapsed, and without that shield, the solar wind stripped away most of the Martian atmosphere over millions of years. The planet became cold, dry, and exposed, and any water it once had either evaporated into space or froze into the ground. Today, Mars is a barren desert constantly bombarded by radiation, a dead world that might once have had a chance at life. Earth could have ended up the same way, but it didn't, because Earth is just the right size. It's massive enough to stay hot inside, with enough internal heat from radioactive decay and leftover energy from its formation to keep the outer core in motion, and because of that, you can step outside without your DNA being shredded by cosmic rays. Let's keep going, because there's more to this story. Earth spins on its axis once every 24 hours, and that rotation does more than just create the cycle of day and night. It keeps the planet's temperature stable in ways that are easy to overlook. If Earth rotated much more slowly, say once every few weeks, the side facing the sun would heat up to unbearable temperatures, while the side facing away would freeze, and the extreme temperature difference would create violent, unstable weather patterns that would make most of the surface uninhabitable. If Earth rotated too quickly, the atmosphere would be thrown into chaos, with winds tearing across the surface and weather patterns never settling into anything predictable. But a 24-hour rotation works perfectly. It gives enough time for heat to build during the day and radiate away at night, and it allows ecosystems to synchronize their behavior with a predictable rhythm. Your body knows this rhythm intimately because you have an internal clock, what scientists call circadian rhythms, that's tuned to the rotation of the planet. When you feel tired at night and alert in the morning, that's not arbitrary or cultural. That's your biology responding to the same cycle that's been running since long before humans existed. And it's not just the rotation that matters, there's also the tilt. Earth's axis is tilted at about 23.5 degrees relative to its orbit around the Sun, and that tilt is the reason we have seasons. As Earth moves around the Sun, different parts of the planet receive more or less direct sunlight depending on the time of year, creating summer in the northern hemisphere, while the southern hemisphere experiences winter and then reversing 6 months later. Seasons aren't just a pleasant variation in weather, they shape everything about life on this planet. They drive animal migrations, trigger reproductive cycles, regulate plant growth, and create the kind of environmental diversity that allows different forms of life to thrive in different conditions. But here's what makes this even more remarkable. Earth's tilt is stable. On some planets, the axial tilt wobbles dramatically over time, shifting from nearly 0 degrees to extreme angles and back again over thousands or millions of years. When that happens, the climate becomes wildly unpredictable. Ice ages come and go rapidly, seasons disappear and reappear, and ecosystems can't adapt quickly enough to survive the chaos. Complex life struggles to gain a foothold in that kind of environment, and long-term evolutionary development becomes nearly impossible. Earth's tilt doesn't wobble like that, and the reason is the Moon. The Moon is unusually large compared to Earth, much larger than you'd expect for a planet of this size, and its gravitational pull acts as a stabilizer. It keeps Earth's axial tilt within a narrow range over millions of years, preventing the kind of chaotic wobbling that would make the climate unpredictable. Without the Moon, Earth's axis would drift, the climate would swing between extremes, and the stable conditions that allowed complex life to evolve and eventually allowed you to exist might never have been possible. So let's take stock of what we've covered so far, because the list is getting long. The right atmosphere, with exactly the right mix of oxygen, nitrogen, and carbon dioxide. Water that expands when it freezes instead of contracting, allowing life to survive under ice. A star that burns steadily instead of flaring or dying out too quickly. An orbit that's nearly circular and sits precisely in the habitable zone. A planet that's exactly the right size to maintain a molten core and generate a protective magnetic field. A rotation speed that creates stable day-night cycles without extremes. A tilt that's held steady by a moon that's the right size and the right distance away. Any one of these factors could have been different, and if they were, you wouldn't be here. Not because you'd be living somewhere else or in a different form, but because you wouldn't exist at all. The conditions required for your existence are so specific, so finely balanced that even small changes would have eliminated the possibility of life as you know it. But there's still more to consider. The air around you right now is pressing down on your body with a force of about 14.7 pounds per square inch. This is atmospheric pressure, and you don't feel it because it's constant, and your body is built to function under these exact conditions. But that pressure is critical. It's what keeps water in liquid form at the temperatures you live in, and without it, water would evaporate far too easily for your body to regulate itself properly. If the atmospheric pressure were much lower, water would boil at room temperature, making complex biological processes impossible. If it were much higher, your lungs might not be able to expand and contract efficiently enough to breathe. 14.7 pounds per square inch is the number that works, and Earth's atmosphere provides it naturally, maintaining this pressure at sea level through the weight of all the air above you. There's also a thin layer high in the atmosphere called the ozone layer, made of oxygen molecules that have been rearranged by ultraviolet light from the sun. This layer does something absolutely essential. It absorbs most of the sun's ultraviolet radiation before it reaches the surface. UV light is dangerous to DNA because it causes mutations that can kill cells or lead to cancer, and without protection from this radiation, life on land would be unsustainable. But with just enough ozone in just the right place, harmful rays are blocked while beneficial visible light passes through, allowing photosynthesis and life to flourish. The ozone layer forms naturally from chemical reactions between oxygen and sunlight, but it can also be damaged or destroyed by certain human-made chemicals, a fact that scientists discovered in the late 20th century. That vulnerability isn't a design flaw, it's a sign that the system is sensitive and finely tuned, dependent on specific chemical balances that can be disrupted if the inputs change. And then there's temperature regulation, one of the most delicate balances of all. Earth's atmosphere contains what are called greenhouse gases, including carbon dioxide, methane, and water vapor, and these gases do something crucial. They trap some of the heat radiating from the planet's surface, preventing it from escaping immediately into space. Without any greenhouse effect at all, Earth would be a frozen wasteland with an average temperature well below zero, making liquid water and therefore life impossible. But if there are too many greenhouse gases, the planet overheats, as we're beginning to see with human-caused climate change. The balance has to be just right, warm enough to support life, but not so warm that the climate spirals out of control. For billions of years, that balance has held. Venus and Mars show us what happens when it doesn't. Venus, roughly the same size as Earth and sitting just inside the inner edge of the habitable zone, has an atmosphere so thick with carbon dioxide that a runaway greenhouse effect has taken hold. Surface temperatures on Venus are hot enough to melt lead. The atmospheric pressure at the surface is 90 times greater than Earth's, and the clouds are made of sulfuric acid. If Earth is a warm cup of tea, Venus is a boiling kettle that never stops screaming. Mars tells the opposite story. Sitting on the outer edge of the habitable zone, Mars has ice and may have had liquid water billions of years ago, but it's cold, dry, and exposed now. When Mars lost its magnetic field, the solar wind gradually stripped away most of its atmosphere, and without that protective blanket, the planet couldn't hold on to its heat or its water. The surface is now a frozen desert bombarded by radiation, a cautionary tale of what happens when the protective systems fail. Earth sits between these two extremes, not too hot and not too cold, not too thick and not too thin, in a narrow band of conditions that makes life not just possible, but abundant. So here's the question this raises, not as proof and not as certainty, but as something worth sitting with for a moment. When you look at all these conditions, all these narrow ranges, all these systems that had to align just right for you to take a single breath, does it feel random? Or does it feel like something was paying attention? Think about it carefully. The air you're breathing right now, mixed to a precise ratio. The water in your cells, behaving in ways that almost no other substance does. The magnetic field you can't see, protecting you from radiation that would otherwise kill you. The spin of the planet, syncing with the sleep-wake cycle built into your biology. the moon in the sky, stabilizing the seasons and the climate, the atmospheric pressure keeping your blood from boiling, the ozone layer blocking ultraviolet rays, the temperature staying within a range where liquid water and therefore life can exist. Any one of these could have been different, and many of them very easily could have been. But they're not. They're all exactly what they need to be, and they've stayed that way for billions of years. You didn't choose this planet. You didn't design these systems. You didn't set the dials or adjust the variables. But here you are, breathing, thinking, alive, sustained by conditions so precise that even a small change in any direction would have made your existence impossible, because everything you need was already here, waiting for you. If the conditions around you are this precise, then the question shifts from where you are to what keeps it all running. Because Earth isn't just sitting in space like a rock. It's active, dynamic, constantly moving and adjusting in ways that maintain the exact environment you need to survive. And the more you look at how these systems work, the harder it becomes to see them as accidental. Let's start beneath your feet, deep inside the planet, where most people never think to look. The ground you're standing on right now isn't one solid piece. Earth's crust is divided into massive plates that float on a hotter, softer layer of rock called the mantle. These plates are constantly moving, drifting across the surface at speeds measured in centimeters per year, colliding with each other, pulling apart, sliding past one another. This movement, called plate tectonics, is what creates mountains, earthquakes, volcanoes, and even entire oceans over millions of years. At first glance, this might seem chaotic or even dangerous, and in many ways it is. Earthquakes can level cities, volcanoes can bury entire regions, and tsunamis triggered by undersea plate movements can devastate coastlines. But without plate tectonics, Earth would be a very different place, and you almost certainly wouldn't be here. If the crust were too thick or the mantle too stiff, the plates wouldn't move at all. The surface would be static and flat, worn down over time by erosion, with no mechanism to rebuild it. Mountains wouldn't form, and without mountains, there would be no rain shadows, no diverse climates, no varied ecosystems. More importantly, plate tectonics plays a critical role in regulating the planet's carbon cycle, one of the most important feedback loops for maintaining a stable climate. When volcanoes erupt, they release carbon dioxide into the atmosphere, adding to the greenhouse gases that keep the planet warm. When mountains are exposed to rain and weathering, chemical reactions pull carbon dioxide back out of the air and lock it into rocks that eventually get pushed back into the mantle through subduction zones where one plate slides beneath another. This cycle acts like a planetary thermostat, preventing the atmosphere from losing all its carbon dioxide and freezing, or accumulating too much and overheating. Without this recycling system, Earth's climate would have drifted into one extreme or the other billions of years ago, and life as you know it would never have developed. But the plates keep moving, the volcanoes keep releasing carbon, the mountains keep weathering, and the balance holds. Not perfectly, and not without variation, but within a range that life can adapt to over time. The soil beneath your feet is another example of precision that's easy to overlook. Soil isn't just dirt. It's a mixture of minerals, organic matter, water and air, and the ratio has to be carefully balanced for plants to grow. Too much sand and water drains away too quickly, leaving plants without the moisture they need. Too much clay and the soil becomes dense and airless, suffocating roots and preventing growth. The best soils, the ones that support forests, grasslands, and the crops that feed billions of people, strike a delicate balance between drainage and retention, between structure and flexibility. And it's not just the soil itself, it's the way life and soil have shaped each other over millions of years in what scientists call coevolution. Plants evolved root systems that match the structure of the soil, while the soil itself was transformed by the presence of plants, enriched by decaying organic matter, and stabilized by root networks. Insects and flowers evolved together, each adapting to the other's needs. Fungi form partnerships with trees, exchanging nutrients through vast underground networks. Bacteria in the soil break down dead matter and fix nitrogen from the air, making it available to plants in a form they can use, This isn't just cooperation, it's integration, where each part has become dependent on the others in ways that make the whole system more stable and more productive than any piece could be on its own. Sometimes the fit between organisms and their environment is so exact that it starts to feel less like gradual adaptation and more like components in a carefully assembled machine. Take something as ordinary as a seed, which you've probably seen thousands of times without thinking much about it. A seed contains everything it needs to grow: genetic instructions, stored energy, and a protective coating. It waits in the soil, dormant and patient, until conditions are right. When moisture, temperature, and light align, the seed transforms. Roots push downward, anchoring into the soil and seeking water. Stems reach upward, breaking through the surface and searching for sunlight. The timing is precise, the sensitivity to environmental cues is remarkable, and the transformation happens with a reliability that makes it seem effortless, even though it's anything but. Even the way seeds are shaped and distributed seems optimized for their purpose. Some seeds are light and equipped with structures that let them ride the wind for miles. Others are heavy and designed to sink into soft soil. Some have hooks that catch on animal fur, hitching rides to new locations. Others are encased in fruit that animals eat, carrying the seeds in their digestive systems and depositing them far from the parent plant, often with a packet of natural fertilizer included. None of this is random. It's the result of millions of years of trial and adjustment, but the end result is a system that works with startling efficiency. Now let's talk about the moon again, because its role goes far beyond just stabilizing Earth's tilt. The moon's gravitational pull doesn't just keep the axis steady, it also creates the tides, the regular rise and fall of ocean levels that happen twice a day along coastlines around the world. You've probably seen tides if you've ever spent time near the ocean, and they might seem like a minor curiosity, but their effects are profound. Tides move nutrients through coastal ecosystems, bringing food to organisms that live in shallow waters and creating unique environments where land and sea meet. These tidal zones may have been essential to the development of early life, providing areas where conditions shifted regularly between wet and dry, encouraging organisms to adapt to both environments and eventually make the transition to land. The moon's influence on tides also affects Earth's rotation in subtle but important ways. The gravitational interaction between Earth and the moon creates friction that gradually slows the planet's spin over time. Billions of years ago, Earth's day was much shorter, perhaps only 6 hours long. Over time, tidal friction has stretched that out to the 24-hour day we experience now, and the process is still ongoing, though at a rate so slow that you'd never notice it in a human lifetime. A billion years from now, if Earth is still here and still spinning, the day will be longer than it is today. This gradual slowing has probably contributed to the long-term stability of Earth's climate, because it means the planet's rotation has stayed within a range that allows for predictable weather patterns and stable ecosystems. If the day-night cycle had been much shorter or much longer, the climate would have been less stable, and the evolution of complex life would have faced additional obstacles. There's also something eerie about the moon's size and distance from Earth. Right now, during a total solar eclipse, the moon appears almost exactly the same size as the sun in our sky, allowing it to block the sun's disk completely while leaving the sun's outer atmosphere, the corona, visible as a glowing halo. This is a coincidence of geometry that won't last forever, because the moon is slowly drifting away from Earth at a rate of about 4 centimeters per year. In a few 100 million years, total solar eclipses will no longer be possible because the moon will appear too small to cover the sun completely. The fact that we exist during this narrow window of time, when total eclipses are possible, is just one more detail in a long list of precise alignments. It doesn't prove anything on its own, but it adds to the sense that the timing of everything, not just the conditions themselves, seems carefully arranged. Then there's gravity, the invisible force that holds everything together and makes all of this possible in the first place. Gravity doesn't get much attention in daily life because it's always there, working quietly in the background. You don't notice it until something falls or until you step on a scale, but gravity is the reason Earth exists as a planet, rather than a loose cloud of debris drifting through space. It's the force that pulled together dust and gas over billions of years, compressing it under its own weight, until pressure and heat created a dense spherical body with distinct layers. Heavy elements like iron and nickel sank to the center, forming the core. Lighter materials floated upward, forming the mantle and crust. Gravity sorted the planet by density, and that sorting still shapes how Earth functions today. Gravity does more than shape the planet. It keeps the moon in orbit, preventing it from drifting off into space or crashing into Earth. It pulls on the oceans, creating the tidal bulges that we experience as high and low tides. It even affects the solid Earth itself, causing slight deformations called earth tides that contribute to stress within the crust and influence tectonic activity over long periods of time. Gravity also locks Earth into a stable orbit around the Sun, a delicate balance between the planet's forward momentum and the Sun's inward pull. If Earth were moving too fast, it would fly off into the cold darkness of interstellar space. If it were moving too slowly, it would spiral inward toward the Sun, eventually burning up or being torn apart by tidal forces. But Earth's speed and position are perfectly balanced, creating a stable orbit that has lasted for billions of years and will likely continue for billions more. On a smaller scale, gravity shapes everything from the flow of rivers to the way trees grow. Water flows downhill because gravity pulls it toward the center of the Earth, carving valleys and canyons over millions of years. Glaciers slide down mountain slopes under their own weight, grinding rock into soil. Even plants sense gravity through specialized cells in their roots and stems, using it as a guide to grow downward into the soil and upward toward the light. And then there's your own body, which is finely tuned to Earth's specific gravitational pull of 9.8 meters per second squared. The strength of your bones, the way your blood circulates, the way your inner ear maintains balance, all of it depends on this exact level of gravity. Astronauts who spend extended time in low gravity experience muscle atrophy, bone density loss, fluid shifts, and changes in vision because their bodies are adapted to Earth's gravity and struggle to function properly without it. If Earth had slightly more mass, gravity would be stronger and bodies might need to be shorter and more robust to support their own weight. If gravity were weaker, the atmosphere might be thinner or even drift away over time, and the planet might not be able to hold onto the water and gases that make life possible. The size and mass of Earth aren't just abstract numbers. They're part of the equation that makes surface life possible, keeping the atmosphere in place, maintaining the hydrological cycle, and creating the conditions where complex organisms like you can exist. Even the way the atmosphere moves is a product of gravity working in concert with Earth's rotation and the energy from the sun. Winds distribute heat, moisture, and particles across the globe, carrying warm air from the equator toward the poles and cold air back toward the equator in vast circulation patterns. Jet streams steer weather systems along predictable paths. Ocean currents interact with air currents, moving energy around the planet and moderating temperatures across different latitudes. Without this constant movement of air and water, the tropics would overheat, the poles would freeze even more than they already do, and most of the planet would be uninhabitable. But the circulation patterns hold, driven by the same forces that have been shaping Earth's climate for billions of years, creating a dynamic balance that adjusts to changes but never spirals completely out of control. And through all of this, the water cycle continues its endless loop. Water evaporates from oceans, lakes and rivers, rising into the atmosphere as invisible vapor. It condenses into clouds as the air cools, then falls back to the surface as rain or snow. That precipitation feeds rivers, recharges underground aquifers, nourishes forests and eventually flows back to the oceans where the cycle begins again. This movement of water is what connects land, sea and sky, distributing resources across the planet and creating the conditions where diverse ecosystems can thrive. The atmosphere is the vehicle for this motion, and it does the job without needing any central control or conscious direction. It works because of temperature, pressure, altitude and sunlight, all interacting according to physical laws that have remained constant since the planet formed, and yet the the result looks like coordination, like a system that was designed to function exactly the way it does. So here's what we're left with when we look at all these systems together: plate tectonics, recycling carbon, and building mountains. Soil that formed through millions of years of interaction between minerals and life. Seeds engineered by evolution to disperse and grow with remarkable precision. A moon that stabilizes the planet's tilt, creates tides, and slowly adjusts the length of the day. Gravity holding everything together and shaping the flow of water, air, and even the growth of plants. An atmosphere that moves heat and moisture around the planet in patterns that keep the climate within livable bounds. A water cycle that never stops, connecting every part of the biosphere in an endless exchange of resources. None of these systems work in isolation. They're all interconnected, each one depending on the others, and together they create an environment that not only supports life, but maintains it across billions of years despite countless disruptions. Asteroids have struck, volcanoes have erupted, ice ages have come and gone, and yet the planet recovers every time, adjusting and continuing. From one perspective, this is just how planets work when conditions happen to be right. From another, it's a finely tuned machine where every part serves a purpose, and the whole system functions with a level of coordination that's hard to dismiss as pure chance. You didn't build any of this, you didn't design the carbon cycle, or create the moon, or set the planet spinning at just the right speed. But you're alive because all of it is here, working together in ways that maintain the exact conditions your body needs to function. And that raises the question again, is this the result of billions of years of random processes that happen to produce a stable outcome? Or does it look like something that was arranged with intention, built to last, and calibrated to support exactly the kind of life that eventually learned to notice it was there? If the planet was set up with this much precision, then the next question is about what exists inside you, because the conditions outside your body are only half the story. The other half is written into every cell you have, in a language that's been running continuously for billions of years without ever stopping, without ever losing its meaning, and without anyone consciously deciding what it should say. At the core of every living thing on Earth, including you, is a molecule called DNA, short for deoxyribonucleic acid. It's a long, twisted chain of chemicals that stores the instructions for building and maintaining your body, and it does this job with a level of organization that goes far beyond simple chemistry. DNA isn't just a substance, it's information, encoded in physical form, written in a 4-letter alphabet made of molecules called adenine, thymine, cytosine, and guanine. These 4 chemical letters, arranged in specific sequences, determine how proteins are made, and those proteins run virtually every process in your body. What makes this particularly striking is that DNA doesn't just store information the way a book stores words on a page. It manages that information actively, turning genes on and off in response to signals from inside and outside the cell, repairing errors when they occur during copying, and regulating itself in ways that keep the entire system functioning. There are sequences within DNA that act like punctuation marks, signaling where a gene starts and where it ends. There are regulatory regions that control how much of a protein gets made and under what conditions. There are repair mechanisms that scan for mistakes during replication and fix them before they can cause problems. All of this happens inside a structure that's only a few micrometers across in every single cell in your body billions of times over, constantly and automatically. The level of organization required to make this work is staggering. Not because it's hard to imagine how it evolved, but because it's hard to ignore how effective it is. Evolution by natural selection provides a clear mechanism for how complexity can arise over time through small changes that improve survival, and the evidence for this process is overwhelming. But even within that framework, the systems themselves stand out for how well they're put together. Consider how proteins fold. Proteins are long chains of smaller molecules called amino acids, and the sequence of amino acids in a protein determines how it folds into a specific 3-dimensional shape. That shape is critical because it determines what the protein can do. If a protein folds incorrectly, it often can't perform its function, and in some cases, misfolded proteins can cause serious diseases. And yet, inside your cells, proteins fold correctly millions of times a day, guided by the sequence of amino acids and assisted by other molecules that act like chaperones, helping the protein reach its proper shape. There's no conscious oversight in this process. No one is checking each protein to make sure it folded correctly. The system works because the rules are built into the chemistry itself, and those rules have been refined over billions of years to produce outcomes that are both reliable and efficient. It's not random trial and error happening in real time. It's the result of a long history of trial and error that has already been filtered through natural selection, leaving behind only the methods that work. Then there are enzymes, specialized proteins that speed up chemical reactions by factors of millions or even billions. Without enzymes, most of the reactions necessary for life would happen far too slowly to sustain a living organism. With enzymes, those reactions happen fast enough to keep cells functioning, to produce energy, to build new molecules, and to break down waste. Enzymes are also highly specific, meaning each one is designed to work with a particular target molecule, fitting together like a key in a lock. This specificity allows cells to control when and how reactions happen, turning processes on and off as needed rather than letting chemistry run wild. There are also molecular motors, tiny machines made of protein that move cargo around inside cells, walking along cellular structures like highways, carrying materials from one location to another. Some of these motors spin like turbines, others pump ions across membranes, and still others open and close gates to control what enters and leaves the cell. They convert chemical energy into motion, often in ways that closely resemble mechanical devices built by human engineers. Except these machines are built from folded proteins and operate at scales far smaller than anything we can manufacture. The more you look at what happens inside a cell, the more it starts to resemble not just chemistry, but engineering. There's the raw code, the DNA sequence itself. There's the machinery that reads and interprets the code, translating it into proteins. There are quality control systems that check for errors and make corrections. There are feedback loops that adjust activity based on changing conditions. There are communication networks that allow cells to coordinate with each other, sending chemical signals back and forth to synchronize behavior across tissues and organs. And just like software, biology has layers. At the lowest level, there's the genetic code, the sequence of chemical letters in DNA. Above that, there's the system that transcribes DNA into RNA and translates RNA into proteins. Above that, there are the proteins themselves interacting with each other to create metabolic pathways, structural components, and signaling networks. And above that, there are the emergent properties, the behaviors and characteristics that arise from all these interactions working together. Things like growth, movement, memory, and thought. The fact that this system is universal across all known life on Earth adds another layer to the mystery. Every living thing, from bacteria to plants to animals, uses the same genetic code with the same 4-letter alphabet and the same translation rules. A sequence of 3 DNA letters, called a codon, codes for a specific amino acid, and there are 64 possible codons but only 20 standard amino acids, which means the system has built-in redundancy. Some codons are synonyms, coding for the same amino acid, while others act as punctuation, signaling where a gene should start or stop being read. This universal code suggests a common origin, some point in the deep past, when life settled on one system, and every lineage that followed carried it forward. But it also raises a question that scientists have spent years investigating. Is this code optimized? Some studies suggest that the genetic code we have is remarkably efficient at minimizing the impact of mutations, meaning that when errors do occur during copying, they're less likely to cause catastrophic changes to the resulting protein. The code isn't perfect, but it's surprisingly good at reducing the damage from mistakes, which suggests that even if it arose through natural processes, it ended up being one of the better possible arrangements. Whether that means the code was selected naturally because it worked better than alternatives, or whether certain structures were simply more likely to emerge and survive, depends on how you interpret the evidence. Either way, what we have now is a system that works across all forms of life and has continued working, with variations and modifications, for billions of years. The question of how this system got started in the first place is one of the most difficult problems in biology. The origin of life, the transition from non-living chemistry to self-replicating, evolving organisms, remains an area of active research with no single accepted explanation. Scientists have proposed various scenarios involving clay surfaces, deep-sea hydrothermal vents, ice-covered lakes, and other environments where the right conditions might have existed for simple molecules to start replicating and evolving. There's been progress in demonstrating that some of the building blocks of life can form naturally under certain conditions, but the full pathway from chemistry to biology is still not fully understood. The challenge is that life as we know it requires more than just the right molecules. It requires systems that can copy themselves, regulate their own activity, respond to their environment, and evolve over time. It's possible that these systems emerged gradually from simpler precursors, with each step building on the previous one. But the transition from random chemistry to organized information processing systems remains one of the biggest gaps in our understanding of life's history. This gap is where some people start to wonder whether biology shows signs of something more than just natural processes playing out over time, not necessarily in the sense of direct intervention or supernatural design, but in the sense that the pieces seem unusually well suited to the roles they play. The genetic code isn't just data sitting inert in the nucleus, it's executable. It runs instructions, modifies itself in response to conditions, and adapts in real time. The system doesn't just store information, it processes it, corrects it, and uses it to build and maintain an organism that can interact with the world. Even the way genetic information is packaged inside the nucleus demonstrates this kind of efficiency. If you stretched out all the DNA in a single human cell, it would be about 2 meters long, yet it fits inside a space that's measured in micrometers, roughly 1/10,000th of a meter across. This is accomplished by wrapping the DNA around proteins like thread on a spool, then coiling and folding those spools into increasingly compact structures, all organized so that the right genes can still be accessed when needed. It's not just compression, it's organized compression where the structure itself is part of the information system. Beyond the DNA, cells contain multiple layers of feedback systems that keep everything in balance. Signals trigger growth when resources are available and shut it down when they're not. Damage sensors activate repair pathways when DNA is harmed by radiation or chemicals. Cells communicate with each other through chemical messages, coordinating their activities to form tissues and organs that function as integrated units. When cells become too damaged or begin behaving abnormally, programmed death pathways can shut them down to prevent further problems. None of this depends on perfection. Mistakes happen all the time. Mutations occur during DNA replication, proteins sometimes misfold, and cells occasionally malfunction. But the system doesn't rely on perfection to keep working. It relies on resilience, on having enough redundancy and error correction built in that occasional failures don't bring everything to a halt. That kind of robustness is one of the hallmarks of well-designed systems, whether they're designed by engineers or shaped by evolution. This is where the comparison between biology and engineering becomes more than just metaphor. When you look at a cell, you're looking at something that behaves like a factory, a city, and a computer all at once. There are production lines churning out proteins, transportation networks moving materials, power plants generating energy, waste disposal systems breaking down garbage, communication networks coordinating activity, and a central archive storing all the instructions needed to build and maintain the entire operation. The question that keeps coming up isn't whether evolution can produce this kind of complexity, because the evidence strongly suggests it can. The question is whether the structure of life, the way it processes information and organizes itself, hints at something deeper than just chemistry following physical laws. Does the fact that DNA behaves like a programming language mean it was programmed? Or is that just a useful analogy for understanding how it works? Does the precision of molecular machinery suggest intentional design? Or is it simply what happens when natural selection refines systems over billions of years? There's no definitive answer, and different people will interpret the same evidence in different ways depending on what they're looking for. But what's undeniable is that life operates according to principles that look a lot like the principles humans use when we design complex systems: information storage and retrieval, error correction, modular construction, where components can be reused in different contexts, feedback loops that maintain stability, networks that allow for coordination across many parts. Whether those similarities exist because life and human technology are both solutions to similar problems, or because both reflect some deeper structure built into the nature of reality itself, is a question that science alone may not be able to answer. But the fact that we can ask it, that we can recognize the patterns and trace the logic, suggests that we're capable of understanding at least some of what's written in the code. And maybe that's the most remarkable part. Not just that DNA exists, or that it works, but that a species that evolved from simple organisms over billions of years can now read the code, manipulate it, and even begin to rewrite it. We've gone from not knowing DNA existed to sequencing entire genomes, editing genes with precision, and synthesizing new genetic sequences in laboratories. In some ways, we've started writing in the language of life, even though we didn't create that language ourselves. It was already here, running in every cell of every organism on the planet, billions of years before we showed up. And now that we've learned to read it, we're starting to see just how intricate, how organized, and how finely tuned the whole system really is. Whether that makes it designed in the traditional sense, or simply the product of a process so long and so refined that it produces outcomes that look designed, is something you'll have to decide for yourself. But either way, the code is real, it's inside you right now, running continuously, managing billions of processes every second, keeping you alive without you ever having to think about it. And whatever its origin, the fact that it works this well across so many forms of life for so long is worth noticing. If all these systems are so finely tuned, if the planet and your body both show this level of organization, then the next question is about timing. Because none of this happened overnight, and the path from a lifeless rock to a world full of complex organisms wasn't smooth or predictable. It was violent, chaotic, and punctuated by disasters that wiped out most of what existed. And yet, every time something catastrophic happened, life came back, often in forms more complex than what came before. Some people call these events accidents, and in one sense they are. A meteor strike isn't planned. A volcanic eruption isn't scheduled. A sudden shift in atmospheric chemistry isn't part of anyone's agenda. These things happen because physics and geology follow their own rules, indifferent to the organisms living on the surface. But the strange thing is how often these accidents, these disasters, that should have been endings, turned out to be beginnings instead. Take the asteroid that struck Earth about 66 million years ago, hitting what is now the Yucatan Peninsula with the force of billions of nuclear bombs. The impact vaporized rock sent shockwaves around the planet, triggered earthquakes and tsunamis, and threw so much debris into the atmosphere that the sky went dark for months or even years. Temperatures plummeted as sunlight was blocked, photosynthesis stopped, and food chains collapsed from the bottom up. Entire ecosystems disintegrated in a matter of months, and by the time the dust settled, roughly 75% of all species on Earth had gone extinct, including nearly all the dinosaurs. That event was not a slow evolutionary process. It was a reset, fast and brutal, erasing millions of years of development in an instant. But it also did something else. It cleared the ecological space that had been dominated by dinosaurs for over 100 million years, creating opportunities for the survivors to expand into niches that had previously been unavailable. Mammals, which had existed alongside dinosaurs but remained small and relatively insignificant, suddenly found themselves in a world with far less competition. Over the millions of years that followed, they diversified, grew larger, developed new adaptations, and eventually gave rise to primates, and from primates to humans. Without that single catastrophic event, the world might still be dominated by dinosaurs, and the lineage that led to you might never have had the chance to evolve. One collision, one moment of destruction, became the pivot point that made your existence possible. And that's just one example. The history of life on Earth is filled with these turning points, moments when everything could have gone differently, but didn't, and each time the outcome, however improbable, led toward greater complexity rather than collapse. Go back further to about 2.5 billion years ago, and you'll find another event that changed everything. At that time, Earth's atmosphere was very different from what you're breathing now. There was almost no free oxygen, and the air was filled with gases like methane, carbon dioxide, and hydrogen sulfide, toxic to most life as we know it today, but perfectly suitable for the microbes that dominated the planet. Then something remarkable happened. Some of these single-celled organisms developed a new way to harvest energy from sunlight, a process we now call photosynthesis, and one of the byproducts of this process was oxygen. At first, the oxygen didn't accumulate in the atmosphere because it reacted with iron dissolved in the oceans, forming rust that sank to the seafloor in massive deposits that we can still see today as banded iron formations. But eventually, the iron was used up, and oxygen began to build up in the atmosphere itself. This event, known as the Great Oxygenation Event, was catastrophic for the organisms that had thrived in the old oxygen-free environment. Oxygen is highly reactive, and for many of those early microbes it was poison. Mass die-offs followed, and the composition of life on Earth shifted dramatically. But the introduction of oxygen also made entirely new forms of life possible. Oxygen allows for much more efficient energy production through a process called aerobic respiration, which produces far more energy than the older anaerobic methods. This surplus energy enables cells to grow larger, to develop more complex structures, and eventually to form multicellular organisms. Without oxygen, complex life as you know it, with tissues, organs, nervous systems, and brains, would be impossible. One biochemical innovation, developed by organisms that had no idea what they were unleashing, changed the entire trajectory of life on the planet, making everything that followed, including you, possible. Around 600 million years ago, another dramatic shift occurred. Multicellular organisms, which had been relatively simple and slow to evolve, suddenly began diversifying at an explosive rate. In a relatively short window of geological time, perhaps 10 to 20 million years, most of the major animal groups that exist today first appeared in the fossil record. This period, known as the Cambrian explosion, saw the development of complex body plans, hard shells and skeletons, eyes, nervous systems, and predatory behavior. It was as if evolution, which had been moving slowly for billions of years, suddenly shifted into overdrive. Scientists still debate what triggered this explosion of diversity. It may have been rising oxygen levels reaching a critical threshold. It may have been the evolution of genetic regulatory mechanisms that allowed for more complex body plans. It may have been environmental changes that created new niches and new pressures for adaptation. Whatever the cause, the timing was narrow, and the outcome was transformative. If conditions had been slightly different, if the oxygen levels hadn't risen quite enough, or if genetic innovations hadn't occurred at the right moment, the explosion of the diversity might never have happened, and complex life might have remained stuck at a much simpler level of organization. Even the movement of continents has played a role in shaping the path life has taken. Plate tectonics doesn't just recycle carbon and build mountains. It also moves land masses around the globe, changing ocean currents, altering climate patterns, isolating populations of organisms, and creating opportunities for new species to evolve. When continents drift apart, populations are separated and evolve independently, often developing into entirely different species over millions of years. When continents collide, previously isolated groups come into contact, compete for resources, and either adapt or go extinct. The formation of mountain ranges changes rainfall patterns, creating rain shadows that turn one side of a mountain range into a desert while the other side remains lush and wet. The opening and closing of land bridges allows species to migrate to new continents, sometimes leading to explosive radiations of diversity, and other times to the extinction of native species that can't compete with the newcomers. Every movement of the plates, every shift in geography, sets new terms for natural selection, determining who survives, who mixes, and who disappears. Then there's the moon again, which we've already discussed in terms of stabilizing Earth's tilt and creating tides, but its origin story is worth considering in this context. The leading theory is that the Moon formed from the debris of a massive collision between early Earth and a Mars-sized object often called Theia. This collision was chaotic, high energy, and probably one of the rarest types of impacts that can occur during the formation of a solar system. The angle had to be just right, a glancing blow rather than a direct hit. The size of the impactor had to be large enough to throw material into orbit, but not so large that it destroyed Earth entirely. The debris had to coalesce into a single large moon, rather than scattering into space or forming a chaotic ring of smaller objects. Any deviation from this narrow set of conditions, and Earth might have ended up with no moon at all, or with an unstable companion that eventually crashed back down, or with multiple smaller moons that couldn't provide the stabilizing influence that the single large moon provides. But the collision happened the way it did. The debris formed the moon, and the system settled into a stable orbit that has lasted for over 4 billion years. Without that unlikely event, Earth's climate might have been too unstable for complex life to evolve, and you wouldn't be here. Biology is also full of what look like lucky breaks when you examine them closely. The appearance of DNA as a stable information storage system, more reliable than the older RNA-based systems that may have come before it. The evolution of proteins with the flexibility to perform thousands of different functions. The emergence of eukaryotic cells, complex cells with internal compartments like nuclei and mitochondria, which likely came from one cell engulfing another not to digest it, but to form a permanent partnership. This symbiotic relationship, where one organism lives inside another and both benefit, allowed for much larger and more complex cells, opening the door to multicellular life. Then there's sexual reproduction, which mixes genetic material from two parents rather than simply copying one, dramatically increasing genetic diversity and speeding up the pace of evolution. Sexual reproduction requires cooperation between individuals, complex behaviours for finding mates, and mechanisms for combining genetic material, all of which are more complicated than simply dividing in two the way bacteria do. And yet, despite the added complexity, sexual reproduction became the dominant strategy for complex life because the benefits of increased genetic variation outweighed the costs. And then, at some point in the last few 100 million years, something even more remarkable emerged. Consciousness. Not just behaviour, not just reflexes or instincts, but awareness, the ability to experience, to remember, to plan, to reflect on one's own existence. Consciousness isn't universal even among animals. Many organisms function perfectly well with simple nervous systems that respond to stimuli without any apparent inner experience. But in certain lineages, particularly in mammals and birds, and in some other groups like cephalopods, something more complex developed. The human brain, with its layered structure built over millions of years of evolution, sits on top of this long biological history. At the base are systems for basic functions like breathing and heartbeat, ancient structures shared with reptiles and even fish. Above that are systems for emotion and memory, structures that became more prominent in early mammals. And on top of all that is the neocortex, the outer layer of the brain responsible for higher level thinking, language, abstract reasoning, and self-awareness. Each layer required earlier systems to already be in place and functioning. The brain didn't appear fully formed, it evolved incrementally, with each addition building on what came before, and at every stage the conditions had to be right. There had to be enough energy available to support the high metabolic costs of a large brain. There had to be social structures that rewarded intelligence and cooperation. There had to be time for these traits to develop and refine, without being wiped out by environmental catastrophes. Looking at all of this together, you start to see a pattern. Life on Earth has faced repeated catastrophes, mass extinctions, atmospheric transformations, climate shifts, collisions from space, yet each time it has recovered, and in many cases has emerged more complex than before. This isn't just resilience, it's a kind of progression, where disasters that should have been endpoints became turning points instead. clearing the way for new forms of life to emerge and filling the world with greater diversity and complexity. From one perspective, this is simply how evolution works when given enough time and enough opportunities. Random variations occur, environments change, and the organisms that happen to be suited to the new conditions survive, while others don't. Over billions of years and countless iterations, complexity accumulates. Not because there's a goal, but because there's always room for something new to emerge in the spaces left behind by extinction. From another perspective, the series of events looks less random and more like a sequence, as if each stage was preparing the ground for the next. The oxygen catastrophe created the conditions for complex cells. The Cambrian explosion created the body plans that would become the foundation for all animals. The asteroid impact removed the dinosaurs and made space for mammals. Each event, however destructive in the moment, opened doors that had been closed before. The term fine-tuning often gets used to describe the physical constants of the universe, the values that had to be just right for matter to form and stars to burn, but it applies just as well to the history of life on Earth. The timing of these events, the sequence in which they occurred, the narrow windows within which each one had to happen for the next stage to be possible, all of it had to line up. Too soon, and the system collapses before it can develop. Too late, and the opportunity is gone. That doesn't necessarily mean it was planned. Randomness can produce sequences that look meaningful in hindsight, especially when you're only looking at the one sequence that actually happened and ignoring all the other possibilities that didn't. But it does mean that the path from lifeless chemicals to conscious beings was not straightforward or inevitable. It was contingent, dependent on a long chain of events that could have gone differently at any point, and the fact that they didn't, the fact that each accident resolved in a way that allowed life to continue and complexity to increase, is at the very least striking. Whether you see this as evidence of design, or as the natural outcome of a process with enough time and variation to eventually produce something interesting, or as something else entirely, the pattern is undeniable. The accidents that shaped life on Earth weren't just obstacles to overcome, they were catalysts, moments when everything changed and the possibilities expanded rather than contracted. And you are the result of every single one of those moments. The inheritor of a history written in stone and bone and DNA, a history that began with simple molecules in ancient oceans and led through catastrophe and survival, innovation and extinction, all the way to a species capable of looking back and asking how it happened. The question now is whether that history is finished or whether you're living in the middle of another turning point. Another moment when the choices made now will determine what comes next and who, if anyone, will be around to look back and ask what it all meant. So where does all of this leave you? You've looked at the conditions around you, the narrow ranges that make your life possible, the precise mix of gases you're breathing, the water that behaves in ways almost no other substance does, the distance from the sun that keeps temperatures stable, the magnetic field protecting you from radiation you can't even see. You've examined the systems that sustain you, the movement of tectonic plates recycling nutrients, the moon stabilizing the planet's tilt, gravity holding everything together in a delicate balance that's lasted for billions of years. You've gone inside your own cells and found a code written in molecules, instructions that build and maintain your body with a level of organization that resembles software more than simple chemistry. And you've traced the history of accidents and extinctions that, against all odds, kept resolving in ways that led to greater complexity rather than collapse. Now the question is what you do with all of that information, because it doesn't come with easy answers or clear instructions. It sits there, a collection of facts and patterns that can be interpreted in different ways depending on what you're looking for. From one perspective, everything you've just considered is the natural outcome of physical laws playing out over billions of years. The universe operates according to rules, matter behaves in predictable ways, and given enough time and enough planets, some of them will end up with conditions that support life. Earth is one of those planets, and the fact that we're here to observe it is not surprising because we couldn't exist anywhere else. This view is often summarized by something called the anthropic principle, which says that of course the universe looks suited to life from where we stand, because if it weren't suited to life, we wouldn't be standing here to notice it in the first place. That's a tidy explanation in many ways, and it's supported by solid science. We know how stars form, how planets coalesce from dust and gas, how chemistry can produce increasingly complex molecules under the right conditions. We know that evolution by natural selection can produce the diversity of life we see around us, and we have mountains of evidence showing how this process has worked over millions of years. We know that the laws of physics are consistent, that they apply everywhere in the universe, and that they don't require any external intervention to function. But there's another perspective that's harder to dismiss once you've really looked at the details, and that's the sense that the precision goes beyond what you'd expect from random chance. Even given billions of years to work with, it's not just that the conditions are right for life, it's that they're right in so many different ways, at so many different scales, in so many interconnected systems that all had to align for you to be here. Change one variable, the tilt of the planet, the strength of gravity, the angle in a water molecule, and the whole thing falls apart. Not gradually, not with room for adjustment, but immediately and completely. This is where the idea of design enters the conversation, not necessarily in the traditional sense of a conscious being drawing up plans, but in the sense that the structure of reality itself seems to favour certain outcomes. Whether you call that a designer, a principle, a tendency, or just the way things happen to be, the result is the same. The universe we live in, and specifically the planet we live on, behaves as if it was set up to support life, and not just any life, but complex conscious life, capable of understanding and reflecting on its own existence. Some people find this idea comforting, because it suggests that life has meaning beyond simple survival, that there's a purpose built into the fabric of reality itself. Others find it unsettling, because it raises questions that science can't fully answer. Questions about intention, observation, and what happens when the test, if there is one, comes to an end. Still others reject the idea entirely, preferring to see the universe as fundamentally indifferent, a place where meaning is something we create rather than something we discover. All of these responses are valid, and none of them can be proven or disproven with the information we currently have. What we can say with certainty is that the conditions for your existence are extraordinarily specific, that they arose through a combination of physical laws and historical events that could have turned out differently at countless points, and that the end result is a world where life not only exists but thrives in forms so diverse and complex that we're still discovering new species and new mechanisms every year. The question of whether this represents design or chance, intention or accident, may be less important than what you do with the fact that you're here at all, because regardless of how it happened, you are the product of billions of years of cosmic and biological history, a temporary arrangement of atoms that became capable of thought, emotion, creativity, and choice. You didn't ask to be born, you didn't choose the planet, or the time period, or the body you inhabit, but here you are, alive and aware, with the ability to shape your own actions even if you can't control the larger forces that brought you into existence. That awareness itself is one of the strangest parts of the whole story. Out of all the matter in the universe, most of it is not alive, and of the tiny fraction that is alive, most of it is not conscious. Bacteria don't reflect on their existence. Plants don't ask why they're here. Even most animals, as far as we can tell, experience the world without the layer of self-awareness that humans and a few other species possess. But you do. You can think about thinking, you can observe yourself observing, you can ask questions about your own origins and purpose, and you can recognize patterns in the world around you that point towards something deeper, even if you can't quite put your finger on what that something is. This capacity for reflection might be the most important variable in the entire equation, because it's what allows you to consider the possibility that life is more than just chemistry, that the universe is more than just matter in motion, and that your choices might matter in ways that extend beyond your immediate circumstances. Whether that's true in some objective sense, whether there really are watchers keeping score, or a purpose built into reality that you're supposed to fulfill, is something you'll never know with absolute certainty. But the fact that you can ask the question, that you can weigh the evidence and form your own conclusions, is itself a kind of answer. It suggests that the universe, or the planet, or whatever process brought you into being, has produced something that can appreciate what it's looking at, something that can find beauty in a sunset, or meaning in a conversation, or significance in a gesture of kindness. That capacity didn't have to exist. The universe could have been filled with lifeless rocks and burning stars and nothing more. But it's not. It produced you, and with you came the ability to notice that the whole thing is strange and unlikely and worth thinking about. So what do you do with that? One option is to live as if it doesn't matter, to move through life focused only on immediate needs and desires without worrying about the larger questions. That's a perfectly reasonable approach, and many people take it without losing anything essential. Day-to-day survival, relationships, work, entertainment, all of these things can fill a life without requiring any grand theories about purpose or design. Another option is to live as if it does matter, to act as though your choices are being observed and evaluated, whether by a conscious observer, by future generations, by your own conscience, or by some standard that exists independent of any specific judge. This approach doesn't require proof that the test is real. It only requires the recognition that living as if it's real produces better outcomes than living as if nothing matters at all. People who believe their actions have weight beyond the immediate moment tend to make different choices than people who don't, and those differences, accumulated over a lifetime, create very different kinds of lives and very different kinds of legacies. There's also a middle path, one that acknowledges the uncertainty while still taking the question seriously. This is the approach that says you don't know if there's a grand design or a cosmic purpose, and maybe you never will. But the fact that you can ask the question means you should act with intention rather than drift through life on autopilot. It's the approach that treats awareness itself as a responsibility, not because someone is forcing you to, but because the alternative, ignoring the strangeness and improbability of your existence, feels like a waste of something precious. Whichever path you choose, or whichever combination of them you end up following, the underlying reality remains the same. You are here, on a planet that seems almost impossibly well suited to support you, inside a body built by instructions written in molecules, with a mind capable of understanding at least part of how all of this works. That situation is rare, possibly unique in the observable universe, and it won't last forever. At some point, your time here will end, and whatever comes next, if anything, will be something you can't observe from where you're standing now. That limitation, the fact that you can't see past the edge of your own existence, is part of what makes the question so persistent. If you knew for certain that this life was all there is, you might approach it differently than if you knew for certain that something else was waiting. But you don't know, and that uncertainty is built into the structure of being alive. You can gather evidence, form beliefs, make guesses based on patterns you observe, but you can't eliminate the unknown variable at the end of the equation, and maybe that's intentional. Maybe the uncertainty is part of the design, a way of ensuring that your choices reflect who you really are, rather than who you think you're supposed to be. If you knew exactly what was being measured and how you'd be judged, you could optimize your behavior to match those criteria, which might produce technically correct actions without any genuine transformation or growth. But if you don't know, if you have to navigate by your own compass without clear external guidance, then what you do and how you treat others and what you build and what you leave behind becomes a much more honest reflection of your character. Or maybe the uncertainty isn't intentional at all. Maybe it's just the natural result of being a finite consciousness in an infinite universe, trying to understand something larger than yourself with tools that were never designed for that purpose. Either way, you're left in the same position, standing on a planet that seems designed for you, living in a body that seems engineered for awareness, facing questions that have no definitive answers but demand to be considered anyway. The most honest conclusion might be that you simply don't know, and that's okay. You don't know if Earth was designed or if it's the result of countless accidents that happen to line up. You don't know if there are watchers or if you're alone in an indifferent cosmos. You don't know if your choices are being recorded or if they disappear the moment they're made. But what you do know is that you're here now, in this moment, with the ability to choose what comes next. at least within the narrow range of options available to you, and that might be enough. Not knowing doesn't prevent you from acting with intention. Not having proof doesn't stop you from treating others with kindness or working towards something meaningful, or appreciating the improbable beauty of a world where water freezes upward and stars burn steadily and molecules arrange themselves into consciousness. You can live as if it matters without knowing for certain that it does, and the outcome of that choice, the kind of life it produces and the kind of person it makes you into, might be its own form of evidence. Because here's the thing about living as if you're part of something designed. It doesn't take anything away from you if you're wrong. If it turns out the universe really is just matter following rules, and your existence is nothing more than a fortunate accident in a vast sea of emptiness, then acting with purpose and care and awareness still made your life better and made the lives of those around you better. You lose nothing by treating your time here as significant. But if you're right, if there is something watching, if there is a purpose built into the structure of reality, then the way you've lived becomes the answer to a question that was being asked all along. So the question isn't really whether Earth was designed for you. The question is what you're going to do with the fact that you're here, regardless of how it happened. The planet will keep turning whether you notice its precision or not. The systems that sustain you will keep functioning whether you appreciate them or not. The code in your cells will keep running whether you think about it or not. But your awareness of all of this, your ability to see the patterns and wonder about their meaning, that's something rare and possibly unique, and it comes with its own weight. You are, as far as we know, the only part of the universe that can look at itself and ask why. That makes you both observer and observed, questioner and answer, the test and the one taking it. And while you may never know for certain if someone is watching from outside, you do know that you're watching from inside, and that might be the whole point. The watchers, if they exist, might not be separate from you at all. They might be you, future versions of yourself, looking back, or the part of your consciousness that observes your own choices, or the collective awareness of a species that has just barely begun to understand what it's looking at. The test might not have a final exam or a clear pass-fail outcome. It might simply be the ongoing process of becoming aware, of noticing the strangeness, of choosing to act as if it matters even when you're not sure it does. And if that's true, then the only question left is whether you're satisfied with the answers you're giving right now, in this moment, with the choices you're making and the life you're building, and the mark you're leaving on a world that seems, against all odds, to have been waiting for you.